Okay, there we go. We're good now to start, right? All right. Hello, everyone from Chile. Here in Santiago de Chile, it's 4:27 p.m. And today we have another excellent seminar on geotechnical engineering. And the guest that we have today is from Canada, Professor Pooneh Maghoul. Professor, how are you? How is everything in Montreal?
I'm fine. Hi. Thanks for having me today. And everything is perfect today in Montreal.
Yes, it's a good day. It's a beautiful day in Montreal today.
Yes, it is.
Very nice. Very, very nice. Professor, because you are from abroad, from Chile, we would like to ask some questions. I wonder if it's okay with you that we ask you some little things.
Of course, if your questions are easy.
Okay, we are going to try to make really easy questions. The first question would be, how Professor Maghoul became Professor Maghoul all the way since the early years of school, university, all the way through now as a professor in Montreal. How it's how did you become interested in geotechnical engineering? That if you can share a little bit of that.
Yeah. It was actually a dream to become a professor when I was still at school. And I was a good student, good in mathematics and physics. Then it was obvious to me that I wanted to become an engineer. And I've never actually wanted to become a, doctor. It was mathematics and physics were actually my passion. Then when I was a kid, to be honest, I didn't know I wanted to become a geotech engineer. I mean, even become a civil engineer. As I told you, I was really passionate about mathematics and physics, and I was open to any, engineering problem, let's say. I got my bachelor degree in civil engineering at the University of Tehran in Iran. And why I chose civil engineering, because I was actually very interested in mechanical engineering and civil engineering, mostly because of, the mechanics behind that. It's very tangible, you can feel it. Then I actually, between mechanical engineering and civil engineering, I chose civil engineering because of earthquake engineering. Then Iran, like Chile, is very earthquake prone. It's a daily, daily I'm exaggerating, but it's actually a common, problem.
No, it's a daily problem here.
Exactly. Then, that's why I actually chose civil engineering. I got my bachelor degree and I did my master's degree in geotechnical earthquake engineering. And why geotechnical engineering and not structural engineering? Because the geotech, the soil mechanics course we had, I love the topics, and mostly because of the chaotic nature of the soil. It's almost unpredictable. And it's not just about the materials, about geomaterials, but the strange behavior that it shows under chaotic loading conditions. Then, especially today with all this climate change, problems we have, we observe more and more, this strange behavior of geomaterials. Then I had this earthquake engineering component in my master's degree research, and I had
that was in Iran.
No, in France.
In France. Okay.
Yeah.
Your master was in France.
Yes, I got a scholarship from the French ministry. Then I immigrated to Paris. I did my master's and my PhD at École des Ponts, Ponts et Chaussées of Paris, which is one of the best, civil engineering schools in Europe. And my PhD thesis was on, again, geotech earthquake engineering. We developed a numerical code called SiteQuake to study seismic side effects. And lots of numerical, development, analytical development, finite element, boundary element. I'm very proud of actually of my PhD work, and I'm glad, of the opportunity I had. Then my master's and my PhD on geotech earthquake engineering, I moved to Canada in December 2010 to start a new chapter. I started my postdoc in collaboration with Hydro-Quebec. I was at Laval University in Quebec City. Then my project had nothing to do with geotech earthquake engineering. It was on cold regions, heat and mass transfer in soil, and energy efficiency of buildings. Then I completely switched, the topic. It gave me helped me actually develop, a vision that engineering is not all about geotech earthquake engineering. It's not all about software development. We have lots of things, lots of problems. Then it was on, as I told you, on cold regions engineering. Then after 2 years of postdoc, I started working in industry in Montreal. I moved to Montreal, and for 2 years, I worked as a geotechnical project manager in industry. And after 2 years, I just missed academic environment. I decided to apply for academic positions. And in 2015, I started as a tenure track assistant prof at the University of Manitoba in Winnipeg, a central part of Canada. Then we moved to Winnipeg, going to west. And I've been in Winnipeg 2015 until 2021. I was 1 year on maternity leave, and 1 year and a half it was the COVID, situation. And in August 2021, we came back to Montreal. Then I started working as an associate prof at Polytechnique Montreal.
I see.
Then a very colorful background, different languages.
A lot of trips also, a lot of house move.
Exactly.
You have had to move a lot of house.
That's
very
true.
Nice. Very nice. Very nice. The years in Winnipeg were too cold, because my understanding is that is the city of the Olympic Games.
Yeah, it is. Winnipeg, Canada, it's cold. The Winnipeg is also
extremely
cold.
Okay.
It's quite cold. But the big difference is that, when it's -15 or -20, maybe you cannot really, it's cold, you cannot go outside. But what is very specific in Winnipeg is long and constant winter. I mean, in East Coast of Canada, you have some fluctuation. For example, for 1 week, you have -10, then 2 days, it's -2, it's 0, it's +1, then you have the opportunity just to breathe a little bit and go outside. But what's very unique in the prairies, Canadian prairies, it's this constant temperature, for long time, for you have -15 and it will not change.
Okay, very nice. Very nice. And what are your current projects? Are you working in very specific project related to cold areas, or you have more diverse projects? My understanding is that you are involved in some mind-blowing projects.
Yeah, I've been working on several topics, from geotechnical engineering to mechanical engineering and to biomechanics, because I think when we deal with geomaterials, natural materials, we can also switch to biomaterials, I don't think there is a big difference between a bone structure and shale. They are both natural materials, complex materials.
You're working with bones?
I actually work on bones and also work on hard tissues. It's a new
Very
project.
nice. Well, they are porous material. So
Exactly. I also work on lunar geotechniques, and I got the idea from my research on permafrost engineering. Then it becomes mechanics of extreme environments. If we want to broaden a little bit, yeah. Then just to tell you, geotechnical engineering can be applied in different fields with different applications.
Very nice. I loved it. I mean, the moon and bones. What an awesome application of geotechnical engineering. It's absolutely possible. Very, very nice. And Professor, just to start your presentation, can we do one more question? The last one.
Sure. Go ahead, please.
With so much geotech, with so many interesting projects, considering the moon and the biomedical components of geotech, do you have any hobby that you like to practice, or any activity that you like to do in your spare time?
Yeah, I have lots of hobbies actually. I read a lot, I love philosophy and I love psychology. Then organizational behavior, they are actually the topics that I love, and I read a lot. I think, who knows, maybe I can one day get at least an MSc degree in this field.
Nice.
I do different sports too. These days, I actually do kickboxing, and it's very good, for stress relief and.
Oh yeah.
Yeah.
Okay.
Yeah, I mean, I try to enjoy, and the work that we are doing, it's not actually work, it's fun.
It's passion, right? It's fun. Exactly. You don't feel you work, you feel that you are doing your passion.
Exactly.
That's the best way to work.
And by the way, I love soccer too.
Oh, you love soccer?
I'm a big fan of Barcelona.
Of Barcelona?
Yeah.
Even these days?
Even these days. This is actually the definition of a good fan,
A good fan, okay. Okay. Okay, Professor. Thank you very much for sharing those all that information. A lot of interesting information. I'm gonna turn off my mic and camera so you can start your presentation. Again, thank you very much for being here with us. It's a real pleasure to have you here sharing your knowledge. Thank you very much again. Just for your presentation, we are seeing the speaker slides. We are not seeing the main slides, Professor Maghoul.
Let's move. When we tried to test it, it was okay.
Okay. I think okay. No. Just try it again. That I remembered one of my students.
Is it okay now?
Taught me how. Yes, there you go. You go.
Great.
Okay, Professor. I'll turn off my mic and camera. Thank you very much.
Do you want me to turn off my camera too, or I?
No, it's fine. No, please keep it on, please.
Sure.
Thank you.
Problem.
As you wish, in fact.
That's fine.
As you wish.
That's fine.
All right. Thank you, Professor.
Thank you. Then, hi everyone. It's a pleasure to have actually this chance today to talk about a very interesting topic. My talk will be on permafrost, a carbon time bomb beneath our feet. And I understand that the audience is very general. Then I try to keep my presentation general too. I have some, mathematics and equations, governing equations at the end of my presentation. But my goal today is just to talk about, some of the most challenging geotechnical problems that we have these days. Permafrost. I know that in Chile you have this issue too, but what I want to actually present today can be a little bit different. Let's start I go through actually my slides, and if you have any questions, please don't hesitate to interrupt me. I already presented me. I told you that I'm an associate prof at Polytechnique Montreal, and before joining Polytechnique, I was at University of Manitoba. I worked as a project manager in geotechnical engineering in Montreal, and I also taught again at École Polytechnique Montreal and École de Technologie Supérieure of Montreal in 2013-2014. I also presented my different research projects, from climate resiliency of northern infrastructure, non-destructive testing development, bio-inspired smart geotechnique, renewable geothermal energy, space planetary geotechniques, and also biomechanics, hard and soft tissues. Then let's start permafrost. Talk a little bit about permafrost. What is permafrost? Permafrost is defined as any ground that remains at or below 0 degrees for at least 2 consecutive years. This is the definition. And here you can see that we only talk about ground. Ground can actually be without any ice inclusion. When we say permafrost, we think that we deal with just ice. But what I want to emphasize today is that we're talking about a ground at or below 0 degrees, even if we don't have ice in it. And that's why we say all the time permafrost thawing and not permafrost melting. Then this is actually the big difference that I want to emphasize. We have permafrost thawing and we have permafrost, and we don't have permafrost melting. It's not actually a good terminology. And normally the top layer of permafrost, normally the as you can see here, the top layer of permafrost, we call it the active layer, which undergoes seasonal freeze-thaw cycles. And beneath this active layer, we have this frozen ground. Sorry, I'm just lost with my pointer. And here you can see that we have, the presence of the permafrost when the temperature actually remains at or below 0 degrees. Then at the top layer, active layer, it can actually undergo seasonal freeze-thaw cycles, and the temperature, of course, varies. And the thickness of this active layer depends on local and climate conditions, such as vegetations at the top surface, soil composition, air temperature, solar radiation, wind speed, and other factors, environmental factors. Then climate warming will lead to permafrost thaw and increase the thickness of the active layer in many different permafrost sites. We can see more and more, what you can see, the coastal erosions due to this warming. We can see lots of, structural failure. As you can see here, this picture is related to Russian Arctic. And what we face, especially in Canada, in these Arctic, countries, these types of failures that we observe, built environment, natural environment. And it's important to say in Canada, northern regions are home to, indigenous communities. Then it's very important for us. And the other thing is that north of Canada, it's rich in, the natural resources. Then again, you see that we want to develop northern regions, but at the same time, we face lots of problems due to climate warming. I started working on this fascinating topic over the last 3-4 years. And with different, PhD students, we had master's students, and we just wanted to see how these climate change affects, northern infrastructure. Why it's important? Because what we have done so far in civil engineering was based on climate stationarity. What does it mean? I don't know if you have had this experience to do very simple geotechnical design and consider boundary condition, this temperature variation at the top surface. Normally what we do is that we just consider a kind of sine function for temperature. We say we are in January, temperature is -5, depending on the location we are, of course. And during summer, for example, in July, the temperature is +25, for example. For each month, we assign a constant temperature, or we can also do your analysis based on daily temperature. But what we want to see is all the time we have this sine function, very smooth and nice, the function that we apply at the ground surface. But the problem is with climate change, it's not the case anymore. We have lots of climate anomalies. We have precipitation. We have the frequency and the intensity of these events have been changed a lot. And we will have more and more climate anomaly in our, in our cities, which are applied to infrastructure. Then this is actually something we call climate non-stationarity. And we cannot keep designing our infrastructure based on climate stationarity. This constancy that we all the time we consider. We have to consider this change. And the other thing I want to tell you, when we talk about climate change, it's not uniform all around the world. There are some regions which are more prone to climate change. For example, according to Canada's Changing Climate Report in 2019, in the Arctic regions, they observed that they reported that temperatures have been warming at approximately twice the rate as the entire globe. This is a phenomenon that is known as Arctic amplification. And also in another study by Isaacson et al. In 2022, they found that the warming rate for the northern Barents Sea corresponds to 2.5 times the Arctic warming average, which becomes 5 to 7 times the global warming averages. Then you see that we have permafrost, this frozen ground, and we have this thermal loading, which is applied to permafrost, which causes lots of problems that I'm going to talk. Here in this slide, what you can see, we did an analysis in Nunavik. Nunavik is here. It's north of Quebec. I'm in Montreal. I live here. And this is actually this table you can see, it's related to these northern regions, northern Quebec, which is actually in permafrost area. And we developed an AI-powered ground surface temperature platform because you know that air temperature is different from ground surface temperature, and it changes over the year. For example, winter ground surface temperature can be warmer or can be cooler. It depends on the seasonal. And again, in our analysis, in our geotechnical design, normally we go with very simple assumption that ground surface temperature is related with kind of n factor, a constant with air temperature. Then we multiply air temperature by a factor, we call it n factor. Or if we want to do more complex analysis, we consider a complete energy balance at the ground surface by considering radiation, wind speed, etc. And again, all these elements, solar radiation, wind, etc., with climate non-stationarity, it becomes very complex to do the analysis and get a more realistic ground surface temperature. Then what we have done with my student Ali in our lab, how we can apply AI to predict ground surface temperature with all available existing data we have, field monitoring data, and climate models, etc. And this is from 2010 to 2099, 2100, let's say, and we are somewhere here. You see that today in 2022, we talk about climate change and the adverse effect of northern infrastructure, but you can see that this is still blue, right? And the problem we can observe is from 2033, 2032, that it really becomes warmer and warmer. It's actually just to tell you that the problem that we will observe, it's not probably today, even though today is already a very bad situation, but what we will observe is in the future, from sometime in the 2030th century. And also, if you want to see the temperature, the ground surface temperature across this northern Quebec, we did analysis for RCP 4.5, RCP 8.5, and here now we are 2060, it goes up to 2100. And what I want to tell you, RCP 4.5 is moderate, it's good, and RCP 8.5 is actually the worst scenario that we can have. And what we have observed so far, unfortunately, we are somewhere here, especially if the countries, they don't want to keep their promises, in agreement with the Paris, actually, agreement we had recently. Then I have another video to show you. I took it from Brandon's Twitter. And again, permafrost, we talk about permafrost. This is the condition of northern infrastructure. As I told you, it's not Photoshop, it's the reality that we have these days. And the house actually sinking down to the ground. And the other thing which is important is, I told you permafrost, we don't need necessarily to have ice inclusion. But in major part of Canada, the conditions is like saturated. The soil pores are filled with water, and in negative temperatures, we have, the presence of ice. And sometimes we have the presence of ice lenses, due to this suction, when we have this freezing, the temperature creates a kind of suction, and it, suck up this water from the ground water to the surface of the soil. That's why we have the creation of these ice lenses, as you can see. And what is more problematic for us is ice-rich permafrost. Those silty soils with fine-grained soils that actually keep water and make, the creation of these ice lenses within the soil. And when they thaw, as you can see, soil completely, lost its strength. Then in Chile, you're familiar with geotech earthwork engineering and the concept of liquefaction. Just try to see it in this term. You have this thawing, pore water pressure will increase. You have a huge amount of water in the soil that cannot be drained easily, because we deal with silty soil, fine-grained materials with, very low hydraulic conductivity. Then you can see, due to this, the presence of water and generation of, pore water pressure, soil can lose completely its strength. And thawing permafrost, as I told you, alters landscapes and threatens infrastructure built on it, such as roads, buildings, pipelines, and the extent of that threat depends on permafrost characteristics, which can vary greatly even over small areas. Then this is actually the permafrost map of Canada. You can see on top the Arctic regions, we have continuous, the permafrost filled with ice inclusion. In the majority of these areas, we have here the brown zone. We have extensive discontinuous, like what you can see, and we have sporadic discontinuous, that we have the presence of ice patches within the ground. Now, when you have linear infrastructure like roads or embankments over a large area passing through these areas, you can see that, for example, here maybe the ground is stable, but if you go, I don't know, 200 meters away from this zone, you can have a huge ice patch in the ground. Then due to climate warming and permafrost thawing, you can have actually instability issues in these regions. Then you see how your infrastructure can deform, in these beneath this linear infrastructure due to permafrost thawing. also talked about this. I'm talking about this northern infrastructure and the issues we have. It doesn't mean that we have not done anything. In Canada, we have been very active in promoting, and bringing new ideas on the table and designing, in a way that our infrastructure be resilient. But the biggest issue we still have is that non-stationarity problem that we have, that we tried to keep the ground frozen, do very good thermal, insulation. But again, we are not sure, as we have observed recently, that we did fantastic design. We have very robust infrastructure, but due to this external loading, climate non-stationarity, several times we still face problems, and we cannot really have, we have not been successful in dealing with this climate non-stationarity in our design. It's not our fault. It is our problem today in all the sectors, and we have to adapt our design by considering this climate non-stationarity in our design. Then so far, I just presented northern infrastructure. Now what I want to do is just to switch a little bit to another topic, which is actually the topic of my presentation. In addition, the high latitude areas, just consider those Arctic or subarctic regions. They are known as a significant potent component in which a large amount of carbon is stored. And permafrost is likely the greatest source of terrestrial carbon sink in human history. It's currently estimated that permafrost stores between 1,460 and 1,600 billion tons of organic carbon, which is distributed in a shallow depth of 0 to 3 meters. And this amount is about twofold the amount of carbon in the atmosphere today. Emissions from permafrost are already estimated at between 0.3 and 0.6 billion tons of carbon each year, which is roughly equivalent to 7% of the world's total carbon emissions from burning coal, oil, and natural gas. And I am almost sure that none of you has heard about, this permafrost carbon emission. And just consider 7% is the 7% of the world's total carbon emissions today in 2022. And just consider the map I showed you, that the blue column, just imagine in 10 years when we will see more effect of climate warming on permafrost degradation, how this situation becomes worse and worse. It's also worth noting that carbon emissions from permafrost, though, are not even fully accounted for in global emissions budgets or into recently updated national commitments for emission cuts made under the Paris Agreement. In this slide, you can see the carbon map of Canada. Then if you remember the permafrost map of Canada, these regions, they are actually permafrost regions. And the dark blue, they are very high, very rich in carbon. And the orange ones, they are actually low, very low in carbon. Then you see that we have lots of, Arctic regions which are very prone to these, the greenhouse gas emissions. Then we have permafrost, negative temperature. We hope so. Which will not be the case considering the trend of climate warming. And we have geomaterials, we have organic components. It is very important because carbon will be released from these organic components, and etc. that I will explain later. Then the other piece of information that I want to share is the cumulative permafrost emissions could reach 150 billion tons of carbon by the year 2100 without aggressive climate policies or climate change adaptation strategies. Then 150 billion tons of carbon, it's huge, but still we don't have this comparison just to see how important it can be. This amount, 150 billion tons of carbon, is nearly half the world's remaining carbon budget. If we want to keep warming under 2 degrees, which is the limit set in international climate agreement. I'm not talking about oil and gas industry or other, sectors, agriculture. I'm just talking about permafrost and the amount of carbon in it. Then if we don't do anything, then you can see that we will have half the world's remaining carbon budget just due to these greenhouse gas emissions from permafrost. Then this process, which is called positive carbon feedback, because we have positive because this carbon greenhouse gas emissions from permafrost to atmosphere, then can shift the permafrost from a sink of carbon to a source of carbon. And this has been already observed in many different permafrost sites like Arctic tundra. Permafrost degradation due to climate warming affects the net balance of carbon in ecosystem and other processes like vegetation, biogenic activities, and consequently greenhouse gases emissions, methane and carbon dioxide to the atmosphere. Then the amount of carbon released from permafrost depends on biogeochemical conditions after thawing. The ground surface temperature is a key of stimulating biogeochemical processes and carbon cycles in a permafrost site. Then you see that it's like fire. I mean, you need to have a factor which is temperature, rise to stimulate these biogeochemical conditions in the ground in permafrost. And what are these biogeochemical, components? It's something that I am going to present. And one of the key components of these biogeochemical processes in the ground in permafrost that regulates carbon cycle and greenhouse gas emissions in permafrost is the microbial activity. Microbial activity is influenced by thermal and hydrological state of permafrost. Temperature, the warmer the better, and again, the presence of water. The microorganisms utilize carbon in order to grow and breathe, which can affect the carbon storage and emission rate from permafrost at a large scale. So, understanding the conditions and processes of microbial activity is necessary to evaluate the impact of microorganisms on permafrost, carbon loss, and global warming. The existence of unfrozen water in permafrost makes the existence of unfrozen water in permafrost makes a mass transfer through the soil and so impact the microbial activity. Then when I say mass transfer, again, we go back to our, foundation. We have frozen ground, we have temperature. Then when permafrost starts thawing, we have the presence of unfrozen water. Then it becomes like, let's say, saturated soil. Then we have automatically this water movement within the ground, right? It is what we call it mass transfer. And this mass transfer and the presence of unfrozen water can be metabolically active in the presence of water, and when the mass transfer in permafrost happens and without having the liquid water available, the microbes' metabolic activity ceases. This is our general, the understanding of this mechanism, that microbes become more active in the presence of unfrozen water. And if we actually stop, the presence of water, the metabolic microbial activity probably will decrease. As in the absence of mass transfer, as I told you, the water and ions will be trapped in the pores and cannot pass over this. Then you see that it's like a coupled system. The effect of temperature on permafrost thaw, the presence of unfrozen water, and the mass transfer we have that can stimulate, these microbial activities in the ground. Then one significant reason of mass transfer in permafrost is the thawing, which happened due to climate change, as I told you. This process makes the mass and heat transfer in the soil, which subsequently leads to metabolic activity of the microbes and the composition of the soil organic matter. In addition to this microbial activity, we have another factor. We have what we call it plant respiration. Then the warmer, the greener, like then we actually with temperature increase, we have more greening, the presence of vegetation. And this autotrophic respiration of plants either can accelerate the greenhouse gas production or decrease it by doing carbon fixation. It's controversial, right? Contradictory a little bit. And it's just to tell you, we still don't know. You can find anything you wish in the literature. Some people, some researchers believe that vegetation, the presence of vegetation and plant roots can fix the carbon within the ground. There are other researchers that say no, even these roots and plant respiration can be a source of carbon. Then during the cold seasons, the snow cover on the soil acts as a thermal barrier that notably reduces the heat exchange between soil and atmosphere. Why it's important? I already told you about climate non-stationarity, about the difference between air temperature and ground surface temperature. And also I told you that temperature is a factor that stimulates biogeochemical, mechanisms in the ground. Then everything starts with temperature increase. Temperature increase in the soil starts with the temperature applied at the ground surface. Then it's very important to find a way to determine this ground surface temperature, which is still, as I told you, a huge, the problem that we have in the design, in geotechnical design. How can we, even today, estimate an accurate ground surface temperature? And now imagine we're talking about 2100, how we can predict accurately this ground surface temperature. There are different factors, as I told you, solar radiation, wind speed, and also the presence of the snow. The snow cover on the ground can act like an insulator. Then it can protect the heat exchange between the soil and atmosphere and air. Then you can see how complicated it becomes. Then snow cover can also act as a shelter for plants, which protect them from freezing. And the ground surface temperature can be close to freezing point during the cold season owing to the snow cover. Even air temperature is -20, it doesn't mean that beneath the snow, the ground surface is -20. It can be close to 0 degree, and the ground can be actually within the shallow depth can be positive. The temperature can be positive. Then very prone to these biogeochemical or microbial activities. Then ecological change across the Arctic tundra biome due to climate warming remains poorly quantified due to field measurement limitations and reliance on coarse resolution satellite data. So the growing community of plants made scientists to think about the effect of vegetation on permafrost carbon feedback. In many areas, there is no certain data which indicates the exact amount of carbon balance in the soil. Plants can impact the degradation process through a process that's called rhizosphere priming effect. This process, termed as microbial plants interaction, which in fact is the change that's causing microbial respiration due to presence of plant roots. We have plant roots, we have microbial communities, and we have organic matter. Then you see again how complex it becomes. Temperature, soil moisture, presence of food, microbial community. On the other hand, it was shown that the existence of plant roots regulate the activity and growth of some specific type of microorganisms in the soil by providing the vital nutrients for microbial growth. So the interaction of plant, soil, is an essential factor to be considered in carbon transport modeling, as it impacts the microbial activity and subsequently the carbon decomposition rate. The researchers also observed the dependency of carbon fixation cycle to temperature changes in summer, and on opposite side, the dependency of carbon loss on temperature changes in winter. Do you remember during my question session, I told you that I love geotechnical engineering because of its chaotic nature, the chaotic nature of soil? It is exactly what I am actually talking about. We have the presence of roots, microbial activity. This, the presence of vegetation cover, snow cover on the ground surface. And we still don't know, because we have not been very successful in doing comprehensive or holistic field measurement just to observe what is going on. That's why I started actually research with one of my PhD students, Nilufer, just to study the thermohydrobiologeochemical modeling of permafrost carbon feedback. And what we want to do, our work actually has different elements, but we want to develop a mathematical model to simulate the carbon transport in permafrost and predict the carbon dioxide flux from the ground surface. Then in our model, we take into account how seasonal temperature variations and climate non-stationarity until 2100, biogenic activity and plant root respiration affect net carbon dioxide production. And microbial and plant roots processes have been also upscaled and integrated with CO2 transport to estimate the carbon dioxide flux from the ground surface due to soil respiration. Then we did, it's actually part of a presentation that we eventually will not really like, but we made, these are actually our assumptions in our numerical model. We have three components: pore water pressure, temperature, and carbon concentration. We considered soil skeleton is homogeneous, isotropic, and linear. Then water transport is actually is described by using Richard's law, and we considered Fourier's law. And the other things we considered, that liquid water content and temperature correspond to freezing drying assumption. What does it mean? We try to apply the concept of unsaturated soil mechanics into freezing soil mechanics. Like freezing acts like drying in soil. These are actually our governing equations. We considered mass conservation by considering phase change. We considered heat transfer again by considering phase change. We have CO2 production and transport in the ground. Carbon production due to root respiration. We consider different factors that depend on temperature, ground temperature, and also microbial respiration, microbial activities that can affect this carbon release. Then our governing equations are coupled to each other. Then you see that, for example, in carbon production due to root respiration, it's related directly to temperature. In temperature, we have lots of parameters related to mass conservation and presence of water, etc. Then we implemented our model in a finite element code, and we have different actually steps to be able to actually run our model, because it's fully coupled with lots of the numerical issues and nonlinearity. And at the end, by implementing these the equations and following this path, we are able to determine the total carbon flux from the soil. We validated our model with different case studies and lab testing for different components of our model. Here I just want to present one case study. Then this is actually a site monitored by NASA. In these Arctic regions, they actually measure these CO2 emissions from Arctic permafrost region. And these actually sites are shown with these yellow spots in the figure during winter. And as I told you, the work has been done by NASA to measure carbon dioxide flux from northern permafrost regions in the depth of 10 centimeters. Then the sensors were placed at 10 centimeters below the ground surface. Then this is actually the temperature variation over the winter. It's what we considered in our model. We had to make some assumptions because from geotechnical point of view, we didn't have access to all the, material properties. We tried to go with very typical, soil properties in this study. And as you can see, the dots and this green line, they are in situ data. This is the regression from this, the in situ data, and the green line is our model. And you see that even by making those assumptions in our model, we are in very good agreement with in situ data. And what is important in this figure, when we approach 0 degree, when we have this warming or permafrost thawing, we have more and more carbon flux. That shows how this actually gas emissions from permafrost can be accelerated due to this, climate warming. Then we are actually still developing our model, and our paper is almost ready. We will submit our paper, very soon, hopefully by the end of this month. The title of the paper is this thermohydro biogeochemical modeling of permafrost carbon feedback. We did lots of, parametric studies just to see how different factors can affect. As I told you, the biggest issue for us to study, the mechanics of permafrost is lack of data, field data. This is very actually hard job. I'm not criticizing the people who work on field monitoring. The biggest issue is that we deal with remote areas with lots of, let's say, harsh environment. And the other thing, it is actually a new field of research. Many people, especially from engineering point of view, we still need to monitor the different, sites. And again, if it's very site specific, even though you can monitor a place, a site accurately with the typical, with a kind of a type of vegetation, it doesn't mean you can apply the same thing in other places. Then it's very important to have a very good understanding of this energy balance, the presence of vegetation on the ground, and also the type of microbial community that we have in the ground to be able to come up with, general or even more specific conclusion. Then thank you very much for your attention. These are the conclusions of my presentation. I'm here to answer your question. If you are still there and you're not sleeping, I'm here to answer your questions.
Thank you very much, Pooneh. Let's see if there are questions, because we have two sources. We have the YouTube and we have the Zoom room. Okay, here on YouTube, we don't have questions yet. Let's see if we are going to have questions in the Zoom room. Eventually, I will give access to, we might change we might switch to Spanish. All right, just for you to know, Professor Maghoul, and I will translate for you.
Sure.
Okay, here we have a question for Doctor. I'm gonna activate the mic for Doctor. He doesn't say the name, but I saw he is a male. Just Doctor. Let me see how. There you go. Let me see. Karina, could you help me activating the audio for the R? I cannot activate it.
On mute. Oh, we have a question in chat.
Okay. But can we check what might be happening with DR just for so he can do his questions afterwards. Okay, engineering Shabir. He asks, can we take fossils as a cause of CO2 below the surface of Earth?
It is exactly what I meant by, the organic matter. Organic matter, they are, the ancient trees, or you said fossils, the animal, the corpse and everything that are in the ground, and they stayed in the ground for hundreds of years and thousands of years there. This is exactly what you mean. Organic matter or fossils or whatever, they are actually a source or cause of CO2 below the surface of Earth. We also have, in permafrost regions, we also have another source of carbon, which is that hydrate-bearing sediments, that we have it actually in many areas on Earth, especially in Arctic Ocean. But it's something that we have not really studied extensively. And I think the biggest issue, at least in these Arctic regions, permafrost regions, is these organic, materials, organic layers, rather than these gas hydrates, bearing sediments that we have in Arctic regions. Yeah.
I see. Thank you very much, Professor. That was the question from engineer Shabir. Dr. Jamal Fakuri, you are there. It seems that you want to do a question out loud, please.
Yes, my question is, how does methane play into the CO2 formula?
Yeah, I mean, if you want to consider methane, we have CH4, right? Then it is one of the issues that we have is methane is more, let's say, dangerous than CO2 in terms of greenhouse gas emissions and warming. And methane becomes CO2. It's something that it's again kind of greenhouse gases. When we say greenhouse gases, they are not just CO2. We have nitrate, we have actually methane, we have other gases. And one of the biggest issues that we have with all this net zero, the concept that countries are dealing with, as far as I know, and maybe I'm mistaken, I don't know, they didn't actually emphasize what is the target, what type of gas we are dealing with. All the discussions are around CO2. We also talk about methane. For example, in Canada, we have these days lots of funding opportunity to deal with methane emissions. But methane is more prone to warming than CO2.
Thank you.
I see. Thank you, Professor Maghoul. Thank you, Dr. Jamal. Nicolas Soto has a question here. He says, I want to ask about the possibility of using the model on other type of soil, like our mollysols in the Central Valley.
You can for sure apply the model to other types of soils, but just you need to adapt it. As I presented, we considered phase change. Then if you, in Central Valley, you don't necessarily have these freezing thawing, cycles. Then it's better for us because we remove one big source of numerical nonlinearity in our model, but the overall concept of model is the same. And with some minor, change, you can definitely use it for other applications.
I see. Thank you very much. Thank you very much. I wonder if there are more questions. Otherwise, I'm going to start asking myself.
Sure.
I have a lot of questions actually, but provided, let me double check that the YouTube. Okay, in YouTube we are waiting for questions. I have a question in the context of a project that we are developing. in the Chilean Patagonia, to the south of Chile, to the very south of Chile. I would say it's in an area with a lot of glaciers, but those glaciers have been in severe retreat in the last years. So far, we have worked on this problem, mainly looking at the mechanical aspects of a huge failure that happened in 2017, approximately 10 million cubic meters. Very, very big, very big. And my question would be, based on the talk, and based on what I have learned, right? As a geotech, we are always learning about the environment and soils. Could it be possible that the CO2 could be, we know that it's trapped in glaciers. That's my understanding. If I am saying something not very accurate, please correct me. So could it be possible that this CO2 trapped in the water, right, in the glaciers, could affect the material at the intersection between the ice and the rock?
I think what I am a little bit aware of, the type of permafrost, or what you said, glacial, in south of Chile. But what is actually very important to consider is the presence of organic matter. As I told you, when
that's the key. Organic matter more than the CO2. Okay.
Yeah, I mean, because these organic matter that cause, this carbon release. It's like a fuel to them. Then if you have, as I told you, when we say permafrost, we always automatically think about ice inclusion in the ground. But it's not necessarily the case.
It's not necessarily. Okay, that's a good point. I didn't know. I always associate permafrost with ice.
Yeah, that's why we always say permafrost thaw and not permafrost melting. This is actually the big difference between these things. And if you remember the map that I showed you, let's bring it here, I think. Yeah. Then here, as you can see, this is the carbon map of Canada, for example. There are some regions, these are permafrost areas too. But you see that in terms of carbon, they are very low. Then just to tell you that, this, for example, when I was in Manitoba, we were here. There were lots of pits, the organic materials that contribute to this, the carbon release, gas emissions from soil. Then it's very important to have all the components: temperature, water, organic materials. And again, when we have microbial community, then they will actually eat or be fed as nutrients and contribute to these, greenhouse gas emissions.
I see. I see. Very, very, very interesting. So, okay, that's very interesting. We might need to study a little bit more on permafrost itself.
I am open to collaborations.
Yeah, of course. Yeah, it's very interesting. We have very interesting soils in the south of Chile. We might have soils that we need way more study than the studies that have been done so far. I mean, everything is under study all the time, right? So it's we need to study definitely a little bit more. Let me double check if there are more questions here now, and here we are still waiting for questions. It seems to me that we are not going to have more questions, at least in the short minutes that you can be here with us. I am assuming that you have other meetings very soon. So I have one last question. So in what direction should the community move in this, based on the experience that you have built all these years of work, and based on the results that you are obtaining? Where do you think should be the direction of this work of geotech, on how geotech and climate change should be addressed? Because we talk a lot about the water, about the effect of contamination, but the soils in themselves are suffering from all this situation that the world is facing. Where should we start looking at, based on the results that the science has discovered lately?
To be honest with you, as a geotechnical engineer, I'm not saying as a permafrost engineer, as a geotechnical engineer, what I want to say, my comment can be applied to any different fields, or applications in geotechnical engineering. What I personally think is, geotechnical engineering is all about observational methods. If you go back to Terzaghi and Peck and everyone, observation is very important in geotechnical engineering, right? Is the key. And we have had lots of, the interesting mathematical models, poromechanics, application of poromechanics in geotechnical engineering. But the biggest issue that we have is lack of observations and reliable field monitoring data. And when you go through really these harsh environments, I think the amount of reliable data we can have in northern regions, I'm kidding, but it's like monitoring the moon. It's something that you can install so many instruments in these regions. You can monitor over 6 months, 7 months, and after that, the instruments stop working because it's harsh environment. Or the connection is not good because we use satellites to transfer data. Then we have a gap of few months, years in gathering data, and no one is there. We deal with remote areas. No one is there to go to the site and, gather or collect the information we need. Especially with this trend in AI application, again, the biggest issue is lack of data. I read a lot of how to tackle climate change using AI, and sometimes I just laugh because we have not enough data. And even recently, we have started really to have like very robust system, the monitoring, networking, and etc. And it's just very recent. 3 years, 5 years, not more than that. And with AI, we need lots of past data to be able to train our model, right? To predict the future. And it's the biggest issue we have in geotechnical engineering. In structural engineering, we are less, sensitive to this problem because monitoring above grade structural elements is much easier. You can see if the sensor doesn't work well, you can go and replace it, right? But in geotechnical engineering, you install, let's say, a thermocouple at 10 meters below the ground. Then if it stops working, you cannot go to the site and replace it, or you want to instrument beneath the center line of an embankment. If the instrument stops working, you cannot really go and replace it. Then I think monitoring, accurate monitoring in this region is very important. Again, as I told you, the physics is very complex. Even measuring the ground surface temperature, it's a big issue in geotechnical engineering. And when we have this climate non-stationarity, we have lack of data, lack of monitoring, strong and reliable monitoring, the networks. I think that should be our future. Really, go through this, technology development, probably collaborate with other fields to be able to make it possible.
Absolutely, very, very interesting. So, but for instance, in a project like yours, you have been able to collect a lot of data, right? A lot of data. I can imagine with all the technologies that you are using, or is still not enough?
No, we have not actually.
Not enough for your special case. I understand that there is a need for way more data, but in the particular case of your work,
it is actually what we do in climate change and northern infrastructure. It is one of the biggest problem. I mean, the biggest actually lack of monitoring data, reliable data that you can use. This is actually the big issue for us. We gathered lots of information, but as I told you, they are not holistic. In geotechnical engineering, you need to know material properties. You need to know the ground conditions. You need to know the energy balance at the ground surface. Then sometimes, for example, many of these projects are done by other fields, by scientists, for example, and their focus of research is different from what we need in geotechnical engineering. For example, the study that I showed you, in those Arctic regions, the study done by NASA, they did fabulous job. But the problem for us, from geotechnical point of view and modeling point of view, we don't have all the data we need to verify our model. Then we should go and pick some typical values for soil properties,
Yeah.
And it's not our fault either. I mean, sometimes we don't have this holistic approach to go and gather what other fields need. It becomes more expensive, it's lack of interest. For example, as a geotechnical engineer, if I want to go and monitor an infrastructure, the data that I gather may not be interesting, to scientists, geologists. They want to study that site, that object, that infrastructure from different points of view. And my field monitoring program is completely different from what they need. Then at the same time, I understand we cannot make, a field monitoring program holistic in a way that everyone can use it. But still, I believe the future of geotechnical engineering will be that, the monitoring and observational methods.
Absolutely. Absolutely. I agree. We have one more question, the last one.
Sure.
Engineer Shabir, he asks, is there any way to release CO2 by digging tunnels?
You mean release CO2 by digging tunnels? Do you mean to storage CO2 or just facilitate this CO2 release? I don't understand what.
The person just say release. Engineer Shabir just say release CO2. No, he is not. There is no specification from Engineer Shabir.
We have lots of this underground energy storage in geotechnical engineering. We use it. We have actually used it for CO2 sequestration, just to keep CO2 in the ground. Again, some mitigation strategies against climate change. Then ground can be a source of a kind of reservoir for CO2. We take CO2 from atmosphere and we just inject into the ground and keep it in the ground. And at the same time, for example, I told you that hydrate bearing sediments. Oil and gas companies, they have this exploration program, and they extract actually energy from subsurface and use it as a source of fuel. We can do whatever you want. Again, if I want to go to permafrost regions, no study has been done, no research has been done, or project has been actually put in place to use this CO2 as a source of, let's say, fuel for the energy use, etc. You can do theoretically whatever we want, but again, it depends on the applications and what we want to do. We want to keep CO2 in the ground and fix it in the ground, or we want to use it as a source of energy.
I see. Sounds good. Sounds so I mean, in a way we are dealing with a new topic, right? And there are a lot of efforts pushing to understand the complexities of climate change. So I'm sure, well, particularly in the case of you with all this interesting information that you have presented, I'm sure that you are full of new ideas how this should continue in particular. So it's very interesting. It's very, very, very interesting. Okay. Engineer Shabir has a clarification about the question. Engineer Shabir says, I ask as per topic that we are on a time bomb below our feet.
These digging tunnels, you know, what I wanted to say by that title was actually just to show how climate change and permafrost thaw can release CO2. Then we don't really go, and we don't want to go and manipulate or stimulate this CO2 release. What we are looking for is to fix carbon in the ground. You know, we don't want to use, we want to fix it. We want to keep it in the ground, but by considering climate change and the trend we have, the trend of climate warming in those regions, which is up to 7 times more than the global average, it's something that I wanted to say by that title, you know, a time bomb. Because if you remember the table that I showed you, 2022, it was still blue. The problem will start in mid-2030s, right? And this is actually the point or the message of my presentation. Then we don't want to release CO2, we want to fix it. Fix it in the ground.
Very interesting. Very interesting. Very, very, very interesting. Professor Maghoul, it seems that that was the last question. I'm looking here for my pointer. And in the YouTube channel, we didn't get questions, but we got a lot of questions here. It seems to me that for the sake of time, of your time particularly, we can finish the presentation. I wonder if you have some last words to share with us, or
thank you very much for your patience and your interest in you know, in this topic. I would love to actually start collaborating with everyone. This is
yes, definitely. Yeah. At University of Chile, we always want to collaborate.
That's awesome. That's awesome. And even the students, you know, if you have any questions, please feel free to contact me. I will be more than happy.
Thank you very much.
To help.
Thank you very much, Professor Pooneh. So with these last words of Professor Pooneh, it's time to say see you soon, because we have some new we're going to have some maybe 1 or 2 more talks, and this was the talk number 10 of the year. So thank you very much, Professor Pooneh, for sharing your expertise with us.
My pleasure.
And it was a great presentation. Thank you very much, and we look forward to seeing you very, very soon, maybe in a conference or maybe in a meeting. Thank you, everyone, and we look forward to seeing you very, very soon in another talk of geotechnical engineering at University of Chile. Thank you very much. Thank you, Karina. Thank you, Karina. Always there, Karina, for us, to assist us with the technical efforts that these events take. So thank you very much. Thank you, Karina.
Thank you.
Bye-bye, everyone.
Thank you.
Thank you.
Bye, everyone.
Bye-bye.